Hello, good evening everyone, and welcome you all to this last session of Thermodynamics tutorial. I am Thananga Sutia and a PhD student at the Center for Atmospheric and Oceanic Sciences at IISc Bangalore. And today we will be doing sums that is related to chemical equilibrium or phase equilibrium. We'll wait one more minute and then we'll start today's class. Yeah. Yeah, I hope you can see my screen. Okay, so let us start. Uh, so this is a very simple question, and probably the very basic start what we have studied in the high school. So this is just to calculate Kc and Kp and to give a brief summary of what happens in a chemical equilibrium. So what it is given that the reaction between sulfur dioxide and oxygen is a key step in industrial synthesis of sulfuric acid. That means sulfur dioxide and oxygen are reacted, and the mixture of sulfur dioxide and oxygen was maintained at 800 Kelvin until the system reached equilibrium. Now the equilibrium mixture contains this much molar of sulfur trioxide, this much molar of oxygen, and this much molar of sulfur dioxide. Now you have to calculate Kc and Kp for these reactions. Now before going that, we need to brush up the basics of chemical equilibrium. Okay, so chemical equilibrium is basically a dynamic equilibrium. Okay, so that means dynamic equilibrium in the sense means some kind of motion is going on, but at the same time you will not see some motion is going on. Suppose like this is a container, and there is a little hole in the container. Okay, and suppose there is liquid here, and you are filling liquid at the rate of m1 dot, and the liquid is going out of the hole at the rate of m2 dot. Now if m1 dot is equals to m2 dot, what you will see basically that the level of the liquid remains the same. You will feel that basically this is like, okay, it's in static, but at the same time the liquid is coming and going out. So this is basically a case of dynamic equilibrium. So now if we consider that this filling of the liquid is the forward, and the going out of the liquid is the backward. So basically what happens in a chemical equilibrium is that this rate of forward reaction is always equals to the rate of the backward reaction. Okay, now suppose there is a reaction here, A plus B. Okay, and at the initial stage what happens, some C and D amount is formed. Now this is a reversible chemical reaction, and remember chemical equilibrium can only be attained for a reversible chemical reaction. Okay, now suppose at the initial stage C and D were 0. Okay, now as time progressed, the number or the quantity of A and B decrease and quantity of C and D increase. Now as quantity of C and D started to form, it started to regain the formation of A and B. So a time will reach when this forward reaction rate, so this is my forward reaction and this is my backward and suppose this my rate of forward reaction is Rf. Okay, and my backward reaction is what? Now there will be a time when these two rates will be the same. Okay, so when these two will be equal, this is basically your chemical equilibrium. This is the simple definition of chemical equilibrium which we already know. Okay, now according to the conservation of mass, okay, the rate of forward reaction is proportional to the product of concentration of reactants, okay, and rate of backward reaction is proportional to the product of concentration of products. Okay, this means what? Then that this RF is proportional to the product of the concentration of A and B, and this RB, it is proportional to the product of the concentration of C and D. Okay, now we can equate RF is equal to, say, the constant of proportionality for forward reaction is Kf times concentration of A into concentration of B. Okay, similarly the rate of backward reaction will be K into B into concentration of C into concentration of D. Okay, now at equilibrium, what happens basically? The rate of the forward reaction is equals to the rate of the backward reaction. So that as a result of which Kf times concentration of A into concentration of B will be equal to Kb times concentration of C into concentration of D. Okay, now therefore Kf by Kb is equal to what? Concentration of C into concentration of D divided by concentration of A into concentration of B. Okay, now this ratio is what we call equilibrium constant Ke. Okay, this is what we call the equilibrium constant Ke. Now this equilibrium constant is of two types. It can be Kc and it can be Kp. Now Kc is when concentration is in terms of molarity, and concentration and Kp is when the concentration is in terms of partial pressure. Okay, so what we have got that there are two types of equilibrium constant, Kc and Kp, and Kc is when the concentration of the reactants and products are in terms of molality, and Kp is when the concentration are in terms of partial pressure. So this is basically applied in terms of ideal gas, okay, or gaseous mixtures. Now suppose that in the earlier case the reaction was very simple, that the number of moles of A, B, C and D were all 1. Okay, now suppose that there were, in the stoichiometric reaction, there were A number of A moles of A, B number of moles of B, and C number of moles of C, and D number of moles of D. Okay, then in that case my equilibrium constant will be nothing but the concentration to the power D stoichiometric coefficients. Okay, because this will be again the product of C into C into C. How many C's? C number of C's, so that will be C to the power C. Okay, fine. Then so then we need to know one more thing, to solve the first question, we need to know the relation between Kc and Kp. Okay. Now what we know basically from ideal gas equation is that PV is equals to N RUT. When number of moles is there, this is basically the universal gas constant. Now you put P aside, this will be basically N by V into RU into T. Now this is basically what? My concentration. Okay, so this is basically what? P of say the element A is equals to concentration of the A times RU times T. Okay, so we can put it here that Kc is equal to, we have got concentration of C to the power C, concentration of D to the power D divided by concentration of A to the power A and concentration of B to the power B. Now we can put this one here. Okay, so what we will get basically, you will get, instead of the concentration of A, you will get PA by RUT, similarly for B and for C and for T. So this will basically give you PC by RUT to the power C, PD by RUT to the power D, and PA by RUT to the power A, and PB by RUT to the power B. Okay, and put this all, you will get basically PC to the power C, PD to the power D to the power D, PA to the power A, and PB to the power B into RUT to the power C plus D, sorry, A plus B minus C plus D. Okay, now this is basically your Kp. Okay, so what we got basically, Kc is equals to Kp into RUT to the power A plus B minus C plus D. Okay, now what people actually remembers is Kp is equals to Kc into RUT to the power C plus D minus A plus B. Now this is also written as Kc times RUT to the power delta Ng, where delta Ng is equals to number of moles of products minus number of moles of reactants. Okay, fine. So let us move back to the question then. So the question that is given is that sulfur dioxide and oxygen reacts to form sulfur trioxide. Okay, so the reaction that is given to us is that sulfur dioxide, and it reacts with oxygen to form sulfur trioxide. Okay, now if you balance it, the stoichiometric equation becomes this form. Okay, so therefore Kc is what? Is concentration of SO3 whole square divided by concentration of SO2 whole square into concentration of O2. Okay, so concentration of SO3 is given as 5 into 10 to the power minus 2, 5 into 10 to the power minus 2 whole square, and concentration of SO2 is 3 into 10 to the power minus 3, whole square, and concentration of oxygen is given as 3.5 into 10 to the power minus 3. Okay, put all these values, you will get the first answer. So the answer is 7.93 into 10 to the power 4. Okay, so then Kp is Kc into RUT to the power delta Ng. Okay, okay, so Kc is 7.93 into 10 to the power 4, and your Ru in terms of liter into atmosphere per mole per Kelvin is 0.08206. Okay, and the temperature is given to us as 800 Kelvin. Okay, and delta Ng will be number of moles in the product is 2 minus 2 plus 1. Okay, so this will give you 1.2 into 10 to the power 3. Okay, next, consider the dissociation of nitrogen molecule into nitrogen atoms at 25 degrees Celsius. Determine the equilibrium constant Kp for the reaction, and then based on the value of Kp, what can you infer for this one? So the earlier question, it was basically a simple where your molar concentration values were given to you, and then you have to calculate the Kc values. But now here you are not given any concentration, you are only given the dissociation temperature, the temperature at which the dissociation is taking place. Now from that, how can we determine the value of equilibrium constant? Okay, so this is the question now. Okay, so for that again we have to go that basically for chemical equilibrium, the change in Gibbs energy at a given temperature and pressure is 0. Okay, so in other words, dg at a given temperature and pressure must be equals to 0. So this is the condition, and this we will apply continuously in order to derive expressions for different conditions. Now suppose you have a vessel okay, that contains four components: A, B, C, D in chemical equilibrium. Okay, so what we did basically consider a vessel containing okay, so consider a vessel containing four components: A, B, C, D in chemical equilibrium. Okay, and let the number of moles be Na, Nb, Nc, and Nd respectively. Okay, now number of moles can be anything. It depends on us how many number of moles we are mixing to make them in equilibrium, but there always be a stoichiometric reaction. That means that this is the simplest form or the skeleton form of reaction, okay, between the two between the four components. Okay, so let the stoichiometric equation be Va times A plus Vb times B gives Vc times C plus Vd times D. Okay, where Va, Vb, Vc and Vd are stoichiometric coefficients. Fine. Then let us assume that the reaction proceeds to right, that means forward reaction, by an amount d epsilon. This means what? That the forward reaction is taking place by an amount d epsilon. Okay, that the forward reaction is taking amount by an amount d epsilon. So therefore the change in number of moles of each component are d n a is equals to minus Va times d epsilon. Why it is minus? Because the reaction is proceeding towards the right, and since the reaction is proceeding towards the right, the forward reaction is taking place. So in case of forward reaction, the number of moles of A will decrease. Similar will be the case for the number of moles of B. Okay, the change in the number of moles of B will be equal to minus Vb times d epsilon. Okay, then change in the number of moles of C will be equal to plus Vc times d epsilon and change in the number of moles of D will be equals to plus Vd times d epsilon. This is D. Okay, fine. So now, therefore, the change in Gibbs free energy at any temperature and pressure will be what? Gc bar dnc plus gd bar dnd plus gb bar dnb plus ga bar dna. So we have got 4 new terms. What are this? The ga bar, gd bar, where ga bar, gb bar, gc bar and gd bar are partial molal Gibbs function. That means per unit number of moles Gibbs function. Okay, so you will multiply with the total number of moles that are changed, then you will get the total change in the Gibbs free energy. Fine. For chemical equilibrium, what we know that dg at a given temperature and pressure must be equals to 0. So that means this entire expression will be equal to 0, and then we will put the values here. Okay, so what you will get basically, gc bar times vc d epsilon plus gd bar vd d epsilon minus gb bar vc vb d epsilon minus ga bar va d epsilon is equals to 0. Or in other case, if you take g epsilon common, so basically this will be equal to the product of stoichiometric coefficient into the molal Gibbs energy. Vd minus gb bar into vb minus ga bar into va is equals to 0. So this is one criterion for chemical equilibrium. Okay, any doubt? Okay, fine. Now again we know what we know. We know that the Gibbs energy G is nothing but your H minus Ts, where H is enthalpy, T is temperature, and S is entropy. Okay, so partial differentiating with respect to Na. I have picked up any component Na. What we have is that delta G by delta Na is equals to delta H by delta Na. Now this temperature will come out. Why? Because we know that when there is an equilibrium mixture, the temperature is same for everyone. So this will be basically delta S by delta Na. Okay, so that means your molal Gibbs energy for the compound A is nothing but the molal enthalpy for the compound A minus temperature times molal entropy of this N. So this is a very important expression from which basically we will be calculating the Gibbs energy. Okay, now for ideal gas mixture, what we know that enthalpy is not a function of pressure. Okay, so therefore your H bar A will be equal to H bar A at a given temperature and pressure, and that will also be equal to your reference enthalpy of the compound A at the given temperature at the reference pressure. Okay, and similarly we know that for ideal gas, entropy is function of both P and T. Therefore SA bar will be equal to SA bar at a given temperature and reference pressure at a given temperature reference pressure minus RU, or basically I can write this universal gas constant as R bar ln YA times P by P0, where P0 is the reference pressure and YA is the mole fraction of A. Okay, so putting these values in this equation, what we get G bar A is equals to H bar of A at a given temperature and reference pressure minus T of S dot A at a given temperature and reference pressure plus R bar T ln YA times P by P0. Okay, now this is what? This is the Gibbs function, molal Gibbs function at the reference pressure. Okay, YA times P by P0. Okay, now again we will put this value of GA in that equation. Say this is my equation A. Okay, so my equation A implies what? DG at a given temperature and pressure will be equal to VC into C plus R bar T ln yc times P by P0, okay, plus Vd times Z dot D plus R bar T ln yd into P by P0 minus Va into Za plus R bar T ln Ya into P by P0 minus Vb into Z bar B plus R bar T ln Yb P by P0, okay, and this whole thing. Now let delta G0 is equals to Vc plus Vd Z bar D minus Va Z bar A minus Vb Z bar B. This is basically what? Gibbs function change. This is the Gibbs function change that would occur if stoichiometric equation completely proceeded stoichiometric equation completely proceeded from left to right, okay. Therefore dg at a given temperature and pressure will be d epsilon times delta G0 plus R bar T ln Yc to the power Vc Yd to the power Vd by Ya to the power Va times Yb to the power Vb into P by P0 to the power Vc plus Vd minus Va minus Vb, okay. Now for equilibrium at chemical equilibrium, dg at a given temperature and pressure is equals to 0. So that means this entire term will be equal to 0. So this, therefore this implies minus delta G0 by RT is equal to ln Yc to the power Vc Yd to the power Vd divided by Ya to the power Va into Yb to the power Vb times P by P0 to the power Vc plus Vd minus Va minus Vb. So we assume this thing as equals to K. Okay, so this is my equilibrium constant. Okay, so therefore ln K is equals to minus delta G0 divided by RT. So we will have to deal maximum number of times in this chapter with this equation. Okay, now let us come back to the equation. Okay, so in our question they are telling us that the nitrogen, it is getting dissociated to 2N. Okay, and the temperature given to us is what was the temperature that is given at 25 degrees Celsius. 25 degrees Celsius, so this is basically your 298.15 Kelvin. Okay, so therefore ln K will be equal to what? Delta G0 RT. Okay, now this delta G0, this is basically a function of the temperature T. Okay, so from here we can write K is equals to e to the power minus delta Z0 at the temperature T divided by R into T, where R, remember, is the universal gas constant. Okay, so let me write this as R1. Okay, now from this equation, this is the stoichiometric equation. Okay, from this equation we have Vn2 is equals to 1 and Vn is equals to 2. Okay, so therefore delta Z0 at a given temperature T, what was the formula? That the stoichiometric coefficients of the product into the molal gives free energy. So this will be basically Vn into Z dot n minus Vn2 into Z dot n2, isn't it? Now Vn2 Z dot n, then this is from the table you can find out, is there 4,555,10, and Vn2 is 1, and from the table this nitrogen, this is equals to 0. Okay, so this will be 9,11,020 kilojoule per kilomole. Okay, therefore K is equals to e to the power minus 9,11,020 divided by 8.314 times 298.15. So this is almost equals to 2.144 into 10 to the power minus 160. So this is almost equals to 0. Okay, so we have calculated Kp or K. Now from this, what can you infer? Now since the equilibrium constant Kp is almost equal to 0, therefore the number of moles of the product formed is very less. How do we know that? Because the equilibrium constant, it is directly proportional to the power of the number of moles. So as the power increases, the Kp increases, and as the value of the number of moles of the reactants increases, the value of Kp decreases. Okay, so this means the number of moles of product form is very less. In short, we can write that is the dissociation reaction this dissociation reaction does not take place at 25 degrees Celsius. Okay, fine. Okay. Okay, so let us go to the next question. Now determine the value of delta G0 and the equilibrium constant for the given reaction at 25 degrees Celsius and 200 Kelvin with water in the gaseous phase. So this reaction is given and they have written this is in the gaseous phase also. So this dissociation reaction is given to us and we need to first calculate the delta G0, and from that we need to calculate the equilibrium constant. You are given the two temperatures, that 25 degrees Celsius and 200 Kelvin. Okay, so what we know that at any given temperature, the standard state Gibbs function change is delta G0 is equals to delta H0 minus T of delta S0. Okay, therefore at 25 degrees Celsius, what will happen at 25 degrees Celsius? Delta H0 will be equal to reactants minus product, isn't it? Sorry, product minus reactants. So 2 times of the H2 plus 1 times of O2 minus 2 times H2. From the table these values are 2 into 0 plus 1 into 0 minus 2 into minus 2, 4, 1, 8, 2, 6. Into 2, 4, 1, 2, 6. 4, 8, 3, 6, 5, 2 kilojoule. Okay. Delta S0 is what? Same, 2 into of H2 plus O2 and 2 into H2O. Okay, so once again you have the values. So this is 2 into 130.678 plus 1 into 205.148 minus 2 into 188.834. 2 into 130.678 plus 205.148 minus 2 into 188.834. So this is 88.836 kilojoule per Kelvin. Okay, therefore delta Z0 will be equal to 48, this value 483652, 483652 minus plus H minus T delta S. So minus T is 25, so this is 298.15 into 88.836, 88.836 kilojoule. Okay. 483,652 minus 298.15 into 88.836. So this is basically 457,166 kilojoule. Okay. Similarly, at 2000 Kelvin, delta H0, this will be equal to 2 of 2000 minus 298 of hydrogen plus H bar 2000 minus H bar 298 of oxygen. Okay, minus 2 of HF0 plus H 2000 minus H of 298 of gaseous water. Okay, 2 into 52942 plus 59176 minus 2 into minus 241,826 plus 72788 kilojoule. Okay, this will give you 503,136 kilojoule. Okay, similarly delta S0 will be equal to 2 into 2000 H2 plus S dot bar 2000 O2 minus 2 into 2000 H2O. Okay, so this is 2 into 188.419 plus 268.748 minus 2 into 264.769. So this will give you 116.048 kilojoule per Kelvin. Therefore, delta G0 is nothing but 503,136 minus 2000 into 116.048 kilojoule. Okay, two 71040 kilojoule. Okay, now the next part, the equilibrium constant. Okay, so ln k at 298 will be equal to minus delta Z0 at 298 divided by R bar into 298. Okay, so this is what ln k at 298, and what we have got at 298 delta G is 457,166 minus 457,166 by 8.314 into 298. So from here you will get K. So 8.08 into 10 to the power minus 81. Okay, similarly ln k at 2000, this will be equal to, at 2000 you have got the 271040 8.314 into 2000. So this implies K at 2000 and this is K at 298. So K at 2000 is what? .33 into 10 raised to the power minus 6. So see the difference between the values of equilibrium constant at two temperatures. So it shows that the temperature should be very, very high for the equilibrium constants to be high. Okay, any doubt you can ask. Okay, now one table is given to us, and the values at the different temperatures for the different reactions, the values of the logarithmic value of K is given to us. That means ln K values are given at the different temperatures for different dissociation reactions are given to us. Now we have to calculate the equilibrium constant for this dissociation reaction. Okay, but can you find this dissociation reaction here? No, we can't find a dissociation reaction here. So how to solve such type of equations now? Okay. Okay, suppose that we can write a reaction three as a linear combination of reactions 1 and 2. Okay, suppose you can write a reaction 3 as a linear combination of two reactions 1 and 2. So that therefore left hand side of the reaction 3 will be nothing but A of the left hand side of equation 1 plus B of left hand side of equation 2. Okay, similarly right hand side of equation 3 will be what? A of right hand side of equation 1 plus B of right hand side of equation 2. Okay, therefore the change in the Gibbs free energy for the reaction 3 will be what? We know that this is nothing but delta Z0 3 of the right hand side 3 minus delta Z0 3 left hand side. Okay, now delta G0 right hand side of the 3 minus left hand side of the 3 is nothing but this one minus this one and this one minus this one. So this will be basically A of delta Z01 plus B of delta Z02, isn't it? And therefore you want to write ln of K for the equation 3. This will be what? Minus delta Z0 of 3 by R bar T. Yes, no? Now just put this value here. What you will get? Minus 1 by R bar T times A delta Z01 plus B delta Z02. Okay, this will be equal to what? A of ln K1 plus B of ln K2. Okay, this I can combine and write this as ln K1 to the power A, K2 to the power B. So therefore the K3 is nothing but K1 to the power A into K2 to the power B. So this is the formula which we have to remember. Suppose you don't know the dissociation value for a given reaction, but you have two reactions with the help of which you can write, or you can write the third reaction as a linear combination of the given two reactions. In that case, we can do this way. Okay. Now let us come back to our equation that is given to us. The equation that is given to us is H2 plus CO2 H2 plus CO2, and this is equals to H2O plus CO. Yes or no? Now let us assume this as my third equation, which I will write as a linear combination of two equations. Now let us find the two equations. Okay, so there is carbon dioxide, so we will find out the reaction which contains the carbon dioxide. This is one, is not it? And then there is water, so we will find out the reaction which contains water. Okay, so let me assume this as my reaction 1 and this as my reaction 2. Okay, so reaction 1 is what? Two CO2 is equals to 2 CO plus O2, and reaction 2 is what? 2 H2O to H2 plus O2. Okay, now how can we write third equation in terms of first and second equation? Take a moment. Will it be half of 1 minus half of 2? I'm sure it is. So that means my A is half and my B is minus half. Okay, so what we know, that ln K3 is equals to ln K1 to the power A, K2 to the power B. Okay, so K1 A and B are equal, but this one, so we can write this as ln K1 by K2 to the power half. Yes or no? Or we can write this one as half ln so what we can write this one as A ln K1 plus B ln K2. Yes or no? Now for the want reaction, ln of K1 value is given, so A is half, and from the table, so we let us assume the temperature is 298 Kelvin. So the first reaction, ln of K1 is minus 207.529 minus 207.529. Okay, then this is minus half times ln of k2 minus 184.420 minus 184.420. Okay, so this will be 529 minus 184.420 into 0.5. So this will be minus 11.5545, or that implies k3 is equals to 9.59 into 10 raised to the power minus 6. Okay, fine. If you have any doubt, you can ask. Okay, so the next question is, determine the temperature at which 10% of diatomic hydrogen dissociates into monoatomic hydrogen at 10 atmospheric pressure. Okay, so the diatomic hydrogen dissociation reaction, the stoichiometric reaction is stoichiometric reaction is H2 to H. Okay, therefore my VH2 is equals to 1 and my VH is equals to 2. Okay, now from this stoichiometric reaction, what we can infer is that 1 kilomole hydrogen H2 dissociates into 2 kilomole H. Okay, let initial composition one kilomole H2, okay, and 0 kilomole H. So initially this was there. Okay, now how many dissociation happened? Okay, let me write this way, it will be fine now. Okay, so initially uh, 1 kilomole and 0 kilomole. Okay, now 10% got dissociated, yes or no? So 10% got dissociated. Change, if 10% got dissociated, so change will be 0.1 kilomole minus, yes or no? and this will give 1 will give 1 will give, that means 1 gives a 2, so that means 0.1 dissociates, so that will be 2 into 0.1 plus. Okay, so final composition will be what? 1 minus 0.1, that is 0.9 kilomole of H2 is there, and 0.2 kilomole of H is there. Okay, so this is the initial concentration. Initially you have 1 kilomole H2 and 0 kilomole of H, which gives to the final composition as 0.9 kilomole H2 and 0.2 kilomole of H. Okay, therefore we know the formula for Kp is what? NH to the power VH divided by NH2 to the power VH2 into pressure divided by total number of moles into VH minus VH2. Okay, so NH is 0.2 and VH is 2, and this is 0.9 to the power 1 into 10 by 0.9 plus 0.2 to the power 2 minus 1. Okay, so this is your 0.404. Therefore ln Kp is what? Minus 0.9063. Okay, now for this dissociation reaction, that is hydrogen, this first reaction hydrogen, so minus we have to find the temperature at which my value of ln of Kp is minus this one. Okay, but in this table we don't have that value directly, so what we need to do, we need to do linear interpolation. Okay, so this will minus 0.9, this will basically lie between 3400 and 3600. Okay, so what we will do by linear interpolation, by linear interpolation, what we will get? 3600 minus 3400 divided by T minus 3400, that will be equal to minus 0.611 minus 1.519. Okay, and that will be minus 0.963 minus 1.519. From here T will be equal to 3400 plus 3600 0 0 minus 3400 times 1.519 minus 0.963 by 1.519 minus 0.611. So from here we will get the answer as 3522.46 Kelvin. Okay. Okay, so let us move to the next question. 1 kilomole of carbon at 25 degrees Celsius and 0.1 megapascal pressure reacts with 1 kilomole of oxygen at 25 degrees Celsius and 0.1 megapascal pressure to form an equilibrium mixture of carbon dioxide, carbon monoxide and oxygen at 3000 Kelvin, 0.1 megapascal pressure in a steady state process. Determine the equilibrium concentration, composition and the heat transfer for this process. Okay, so let us first see what is happening basically. So you have given carbon plus oxygen, okay, and there they underwent combustion, okay, and this gave rise to the formation of carbon dioxide at 25 degrees Celsius. Okay, after that this carbon dioxide got some amount of heat, due to which heating and dissociation take place. Okay, due to this heating and dissociation, once again they came back and at around 3000 Kelvin, okay, there was mixture of A number of carbon dioxide plus B number of carbon monoxide and D number of oxygen. Okay, so these were the products and these were the reactants. Okay, and this was at around 25 degrees Celsius. Okay, so this is my control surface, and from here some amount of heat is getting released. Okay, so basically what is happening, that initially combustion reaction happened. Okay, so what happened in the combustion reaction? C plus O2 simply resulted in the formation of CO2. Okay, so combustion reaction was formed, but as it got heat, there was also another reaction called dissociation reaction also took place, because you were adding more and more amount of carbon dioxide, more and more amount of heat. So this dissociated carbon dioxide got dissociated into carbon monoxide and oxygen. Okay, so if you balance this one, so basically that is the energy released by combustion of carbon and oxygen heats the CO2 formed to high temperature which causes dissociation of part of CO2 to CO and oxygen. Okay, so therefore the overall chemical reaction is what? C plus O2, which gives A number of CO2 plus B number of moles of carbon monoxide plus D number of moles of oxygen. Okay, now suppose the combustion reaction take place. Okay, so initially how many number of moles of carbon dioxide was there? One number of moles of carbon dioxide, because this reaction has got one. Okay, so and you are reacting 1 kilomole of oxygen to 1 kilomole of carbon. If you react 1 kilomole of oxygen and 1 kilomole of carbon, you will get 1 kilomole of carbon dioxide. So from combustion reaction, the initial composition of carbon dioxide for dissociation reaction is how much? 1 kilomole CO2. Okay, so that means now let the number of moles of carbon dioxide dissociated is equals to 2Z. Okay, so the dissociation reaction, what we can write? 2CO2 2CO plus O2. So what happened in the initial state? There were 1 kilomole and 0, 0, isn't it? So change, we have taken this as 2Z was gone. So if minus 2Z is gone, so this will result in the release of the plus, formation of plus 2Z, and this will result in the formation of Z. Okay, so then final or at equilibrium, what happened? The number of moles of carbon dioxide that is present is 1 minus 2Z, the number of moles of carbon that is present is 2Z, and the number of moles of oxygen that is present is Z. So basically we have got the values of A, B and C. The value of A is this one. This is basically my value of A. This is basically my value of B. And this is basically my value of D. Okay. Therefore, total number of moles or N is equals to 1 minus 2Z plus 2Z plus Z. So this is equal to 1 plus Z. Okay. Therefore, mole fractions at equilibrium, Y CO2 that will be equal to number of moles of the carbon dioxide divided by total number of moles. Similarly, Y carbon monoxide will be equal to 2Z by 1 plus Z, and Y of oxygen will be equal to Z by 1 plus Z. Okay, now from table, the dissociation value of equilibrium constant at now this reaction. Okay, so this reaction, and temperature value is given to us at 3000. Okay, so at 3000 it is minus 2.217 ln of K. Okay, ln of K is equals to minus 2.217 at what? 3000 Kelvin. Okay, so therefore we can get K is equals to e to the power minus 2.217, which will be equal to your 0.1089. Okay, again we have already derived the value of K is nothing but YCO to the power VCO into YO2 to the power VO2 divided by YCO2 to the power VCO2 into P by P0 to the power VCO plus VO2 minus VCO2. Now what we have, the values of VCO2 is equals to 2, VCO is equals to also 2, and VO2 is equal to 1. Okay, okay, so and P is given to you as 0.1 megapascal, which is approximately equal to 1 atmosphere, and P0 we already know this one as 1 atmosphere. Okay, so therefore K is equals to what? 2Z by 1 plus Z whole square into Z by 1 plus Z by 1 minus 2Z by 1 plus Z whole square into P by P0 is 1. Yes or no? And this K we already know this one is 0.1089, and this will be equal to 4Z cube divided by 1 minus 2Z square into 1 plus Z. Now since number of moles must be greater than 0, so Z should be greater than equal to 0, and also this Z should lie between 0 and 0.5y because of this constraint. Okay, so we'll solve a cubic equation, and you will get the value of Z is equals to 0.2189. Therefore my A is equals to 0.5622, my B is equals to 0.4378, and my D is equals to 0.2189. Therefore the full equation or the reaction, therefore the overall reaction is what? C plus O2, this gives 0.5622 CO2 plus 0.4378 CO plus 0.2189 O2, and also the mole fractions Y of CO2 is nothing but 0.5622 by 1.2189, that is equal to 0.4612. And Y of CO is equals to 0.4378 by 1.2189, which you will calculate and you will find it as 0.3592, and Y of O2 is equal to 0.2189 by 1.2189, and that is equal to 0.1796. So these are the concentrations at the equilibrium. Okay, now we have to calculate the heat transfer, the second part of the question. So calculation of heat transfer. Okay, so the heat transfer will be nothing but HP minus HR, where HP is enthalpy of products and HR will be equal to enthalpy of reactants. Okay, so now enthalpy of reactants HR. So the reactants are these are, okay, carbon and oxygen. Okay, and the reaction takes place at 25 degrees Celsius. So we know that at 25 degrees Celsius the enthalpy of formations are almost zero. So therefore HF0 for C plus HF0 for O2. So this will be 0 plus 0, and that is equals to 0. Okay, now enthalpy of products. Okay, so the number of moles we have got, this is the overall reaction. Okay, this is the number of moles, and then the product, and the products formed are at, remember, these are formed at a temperature of 3000 Kelvin. Okay, so the enthalpy of the products will be number of moles of carbon dioxide times enthalpy of formation for this one plus 3000 minus 298, this is for carbon dioxide, plus number of moles of carbon monoxide, and same will be this one formula, plus 3000 minus 298, this is for carbon monoxide, and also the oxygen number of moles, 298, and this is for oxygen. Okay, so number of moles of carbon dioxide we have found it 0.5622, and these are all from the values, the book that is recommended. The values are given straight away there. So it is 39352 plus 152.853 plus number of moles of carbon monoxide is 0.4378 into minus 110527 plus 93504, and number of moles of oxygen is 0.2189 into 98013. You put all these values, you will get this as minus 121302 kilojoule. So therefore this value is minus 121302 kilojoule. So this is the amount of it that is released by when this reaction is formed. This reaction is formed. This is the combustion chamber, and here from here to here the enthalpy change is basically this amount of heat that is released into the surroundings. Okay, fine. So let us move to the next question now. A mixture of 2 kilomole of carbon monoxide and 3 kilomole of oxygen is heated to 2600 Kelvin at a pressure of 304 kilopascal. Determine the equilibrium composition assuming the mixtures consist of only carbon dioxide and water. This is just the similar question. In the previous case, the combustion chamber, combustion was taking place between carbon and oxygen. Now the combustion is taking place between carbon monoxide and oxygen. Now let us first look at the stoichiometric reaction, the combustion stoichiometric reaction. Okay, so this will result in the formation of carbon dioxide. Now if you balance this, this will be 2 and this will be 2. So that means in the stoichiometric mixture, if 2 kilomoles of carbon monoxide reacts with 1 kilomole of oxygen, it basically results in the formation of 2 kilomoles of carbon dioxide. Okay, but now the initial stage, the combustion chamber has 2 kilomoles of carbon monoxide and 3 kilomoles of oxygen. Okay, there is 2 kilomoles of carbon monoxide and 3 kilomoles of oxygen. So this is the stoichiometric combustion reaction. But now initial condition we have how much? 2 kilomoles of carbon monoxide and 3 kilomoles of oxygen. Okay, so that means 2 kilomoles of carbon monoxide will react with 1 kilomole of oxygen to form 2 kilomoles of carbon dioxide, and the remaining oxygen will remain as it is. That is 2 kilomoles of oxygen will be remaining unreacted. So this is the initial condition, of dissociation reaction. Why? Because now this part will only get dissociated, the carbon dioxide will only get dissociated into carbon monoxide and oxygen. So as a result of which the product will only contains of carbon dioxide, carbon monoxide and oxygen. So some part of carbon dioxide will get dissociated into your carbon monoxide and oxygen. So we will write the dissociation reaction. The dissociation reaction is carbon dioxide dissociates to carbon monoxide and oxygen, and we balance this. So this, so the initially how many moles of carbon dioxide was there? 2 from here. Okay, and how many moles of carbon monoxide was there? 0. And how many moles of oxygen were there? 2. Okay, now let us assume that minus 2z, that means 2z number of moles of carbon dioxide got dissociated. So that means the change in the number of moles of carbon dioxide is minus 2z. So there will be an addition of 2z of this one, and there will be an addition of z of this one. Okay, so therefore at equilibrium we have 2 minus 2z, okay, and this is 2z, and this is z. So this many number of moles of uh, carbon dioxide, carbon monoxide and oxygen are left. So therefore the overall reaction I can write this overall reaction as 2 CO2 plus 3 O2. Okay, this gives your 2 minus 2z number of carbon dioxide plus 2z number of carbon monoxide, and this is 2 plus z, sorry, and 2 plus z number of oxygen moles. Okay, okay, now this dissociation reaction, just like the previous example, this dissociation reaction in table number here is this one, and at 2600 Kelvin the ln K value is minus 5.594. okay, at 2600 Kelvin, okay, my ln K value is what? Minus 5.594. okay, so from here my K value will be what? K value will be your 3.72 into 10 raised to the power minus 3. okay, now at equilibrium total number of moles N is what? We have already got it, 2 minus 2z plus 2z plus 2 plus z, isn't it? 2 minus 2z plus 2z plus 2 plus z. okay, so this is 4 plus z, and also y CO2 is equals to 2 minus 2z by 4 plus z, and y carbon monoxide is 2z by 4 plus z, and y oxygen is 2 plus z by 4 plus z. okay, so from here also we can calculate K is nothing but y CO to the power VCO into y O2 to the power VO2 divided by y CO2 to the power VCO2 into P by P0 to the power VCO plus VO2 minus VCO2. okay, now P is given as 304 kilopascal, so which is approximately equal to 3 atmosphere, and we already know that P0 is equals to 1 atmosphere. okay, and then VCO from the dissociation reaction is equals to 2, and VO2 is equals to 1, and VCO2 is equals to your 2. okay, so putting all these values you'll get what? 3.72 into 10 raised to the power minus 3 is basically equal to 2z by 2 minus 2z whole square into 2 plus z by 4 plus z into 3. Now if you solve this, z you will get as 0.05. Okay, now if z is 0.05, y CO2 will be equal to what? 1.9 by 4.05, which is equal to your 0.469. okay, and y CO is equals to 0.1 divided by 4.05, which is equal to your 0.024, and YO2 is equals to 2.05 by 4.05, which is equal to 0.5062. okay. Fine. So let us move to the last question. Now at a temperature T and a pressure 1 atmosphere, the equilibrium mixture dissociation for the dissociation of CO2 to CO and O2 contains terms of mole fraction. This given. Okay, so determine the temperature. So what it is given, the dissociation reaction it is what? 2CO2 to CO plus O2. So therefore VCO2 is equals to 2, VO2 is equals to 1, and VCO is equal to 2. okay, now at equilibrium what it is given, that YCO2 is equal to 0.553. okay, YCO is given as 0.298, and YO2 is given as 0.149. okay, and P0 is given as 1 atmosphere, and we already know this, and also our P is given as 1 atmosphere. Therefore my K value is what? YCO to the power VCO into YO2 to the power VO2 by YCO2 to the power VCO2 into P by P0 to the power VCO plus VO2 minus VCO2. okay, hello, yeah, can you 642, can you keep it in the security? 642 okay. So this will be, just put all the values, 0.298 square into 0.149 divided by 0.553 square into 1, and from here your K value will be 0.04326. okay, now from here you will get ln k is equal to minus 3.14. Now you need to check in the table the temperature corresponding to this value, but again we will not get this value, so we will apply linear interpolation, and by linear interpolation you will get 3000 minus 2800 divided by 3000 minus t is equals to minus 2.217 minus 3.781 by minus 2.217 minus 3.140. Okay, so from here your t is equal to 2881.969 Kelvin. Okay, so with this I finish today's class. Hope you all understood, and in case any doubt you can ask me in this email address. I will upload these videos tonight, and also I will share with you the slides of today's class, and I hope you all understood within this 2 weeks of class. It was my first experience as a TA in this platform, and there were a lot of what you call not a proper method of teaching from my side, but I have given everything, and hope you found it interesting. So I'll wait for a couple of minutes if you have any doubts, and then I will just close this class. Okay, thank you.